All right. Good afternoon. We have exam this coming Thursday. It's coming on the science center. We are going to start at 2:10. So, I posted the sample exam with solution on Canvas, so you can take a look. Study very well for this exam. Prepare a good equation sheet, one sheet both sided. So today we are gonna start acceleration analysis for mechanism. Today and on Wednesday we are gonna finish it, hopefully. And next week we are gonna talk about force analysis. Then after we finish the force analysis, we are ready to start kinematic synthesis. How can we design mechanism? Because so far we just did the analysis. We are given with mechanical mechanism, and we just did the analysis for displacement, velocity, acceleration, and force. Then we will learn how to design a mechanism from scratch to do a task for us. So when we start covering this chapter or this topic, it's time for you guys to pick a project and finalize it with me. Then start working on the design process. All right, let's look at the acceleration. So this is the acceleration analysis of mechanism. Before we go through that, let me talk briefly about comparing two vectors. If we have point P, I can connect the origin, which is O, to point P and make a vector OP, and the length of this vector is R and the angle to the ground line is theta. So X component of point P is R cosine of theta. Y component of P is going to be R sine of theta. So this is what we learned so far. So if I provide point B and say point B has A cosine of theta as X component of point B and A sine of theta as a Y component of point B. What can we say about point B and P? What can I say about point B and P?
They have the same angular velocity?
I mean, I'm not talking about velocity. I just have 2 points. No matter if we are talking about dynamics, it's just the coordinates of point P. For point P, if the length of the vector is R, the X component of that is R cosine, Y component as that point is R sine of theta. I introduce another point. This is the X component and Y component. But it has A cosine of theta and A sine of theta.
So they share, if we talk in polar coordinates, they have the same angle with different distances from the origins.
That's true. We can say theta here and theta there. So it tells me these 2 points, point P is going to be on the same direction of point P, but with a different magnitude of distance, which is A. Suppose A is greater than R, point P is going to be somewhere up there. But these two vectors, OP and OB, they are going to be on the same direction. If I introduce point C, one x component of point C, for example, is C cosine of theta plus 90. Y component of point C is C sine of theta plus 90. This is representing this distance, and this is representing the angle of point C from the graph. So as you see, it's 90 degree up from the theta. So whatever is theta, you add 90 degree, which is this. So the angle would be theta plus 90, and point C is going to be somewhere here if this distance is C. Make sense? I'm going to use this on acceleration analysis. It's the reason that I reviewed this first. Any questions so far? All right. Now, let's look at point P, which is moving along this general curve. This is a general curve, and point P is moving along this curve. If I connect point P to origin, I'm going to have this vector with the angle of theta. So if I write the x component of point P, it's going to be r cosine of theta, and y of P is r sine of theta. This is the location of point P. To derive the velocity equation, I differentiate both sides with respect to time. How fast velocity of point P is changing to time, we represent that with x dot of P, or d of xp dt, or velocity of point P in x direction. Right hand side, I should differentiate this with respect to time. R is varying with time. It's going to be r dot cosine of theta plus, now r times derivative of cosine of theta, which is going to be r e of cosine of theta with respect to time. Theta is different than time. I should use the chain rule. It's going to be r dot cosine of theta minus r theta dot sine of theta. This is what we did for velocity. And y dot of P, I differentiate the first term, r dot sine of theta plus r theta dot cosine of theta. Now, I would like to see what would be the acceleration of point P, or how fast the velocity is varying with time. I represent that with x double dot of P, or derivative of velocity of point P with respect to time, or acceleration of point P in x direction. A with the index of px, p representing point P, and x is representing direction of the acceleration. And y double dot of P is going to be how fast the velocity of point P in y direction is varying with time, or a p y. So as class activity, I'm asking you to differentiate these. Just differentiate the first one. I'll do this for y component. Differentiate the x component of acceleration at point P. You are gonna differentiate velocity at point P with respect to time. Make sense? What should be the first step? I just want to see what would be your approach and make sure that you can differentiate the term to derive the acceleration.
Differentiating the x and y double prime once you get to the double circle.
Yes.
So that makes sense.
Okay, let me call some number 33.
Is it r double dot cosine theta?
Would you come to the board and write it down? Any term which is varying with time, you should differentiate that. So R dot, derivative of R dot means R double dot. How fast the velocity or that distance is changing. R double dot times cosine of theta. Okay. Would you differentiate this term and this term, or these two are for this one?
What do you mean?
I mean, you differentiate this guy, this term with respect to time.
Yeah.
So the output will be this. Okay, thank you. Number 32, Alex. Would you come to the board and if you want to change? You can write it down here. That's perfect. You kept the first term. Would you just differentiate one by one and then at the end you can add them all?
No.
You don't mind.
Can I go look at my notes again?
Sure. You should differentiate these two terms with respect to time, one by one. The first variable is r dot. The derivative of r dot will be r double dot times cosine of theta. So second variable is theta. Thank you. Number 35. Yes.
I agree.
Which one? Let me, all right.
Second one.
Second one. Any different out? Yes. Any different out?
For that?
Yes.
Oh, yeah. You actually get to, how am I supposed to
This one. Okay, let me differentiate that. Please follow up if you have any question about this and you have any difficulty about how we can differentiate the acceleration equation. It's time to ask. So I have velocity equation in x component. I'm gonna differentiate that with respect to time. So r dot, it's the first variable. The derivative of r dot with respect to time is gonna be r double dot times cosine of theta. I differentiate this with respect to time times this. Plus, now I should differentiate this with respect to time and I keep this one here. R dot, derivative of cosine of theta with respect to time. Minus, the first variable is r. I differentiate this with respect to time. How fast r is varying with time, I represent it with r dot. Theta dot, sine of theta. Second variable is theta dot. I'll keep r here. Derivative of theta dot, how fast the angular velocity is varying with time, is going to be theta double dot multiplied by sine of theta. Now, last term that I should differentiate with time is sine of theta. It's going to be r dot, not r dot, r theta dot, derivative of sine of theta with respect to time.
Wait, isn't that you're supposed to, where you put the sign at the right, it's supposed to be exactly that, like a derivative of sign.
Yeah.
Yeah.
I differentiate theta dot with respect to time. I have theta double dot.
What did that do?
Multiply.
Yeah. I thought you would be doing the derivative of sine.
I have it here.
Also, there's a whole other.
Yes, plus one negative. So I have three variables: r theta dot and sine of theta.
Oh, because it's three variables now. This is going to be like
Three times. We should differentiate first this, multiplied by these two.
Also, it's a whole other.
Then if I'm gonna differentiate theta dot times this, then I'll keep the first two, differentiate the last term, which is sine of theta. Thanks for making.
I thought that you do it all in one.
No, I mean we have three variables.
Three variables.
We should differentiate first one, multiply by the other two. Then go to the second one, multiply by first one and third one. And then we go to the last one, multiply by first two, which is this guy. Any questions on this? So let me do some math here. So r double dot cosine of theta. Derivative of cosine of theta with respect to time, we use the chain rule, it's going to be negative r dot theta dot sine of theta. R dot theta dot sine of theta. Negative, I have this guy, r dot theta dot sine of theta. Negative r theta double dot sine of theta. And last term is this guy. Derivative of sine of theta with respect to time is going to be negative r theta dot cosine of theta. So x component of acceleration of point P is going to look like this. R double dot cosine of theta. I have negative r dot theta dot sine of theta. I have negative r dot theta dot sine of theta. So I can add them up. Done with these three. Let me first write this term and then I write this one. Negative r theta dot times theta dot. And last term I'm going to have negative r theta dot sine of theta.
What do you add with the bottom?
It's a negative r theta dot times theta dot.
Also square.
Yeah, it's going to be a square. I just wrote this one first, then I added this. Question on this? I'm going to differentiate this with respect to time. Yes.
But if we're gonna like do equations, how should we apply?
If on your mechanism this is not changing, I'm generally speaking, because this is the most general case that you may see. The length of the link, the angle, both are varying with time. But for example, in 4-bar mechanism, this is constant. So R double dot, R dot would be 0. This time is 0, you end up with this. Make sense?
Yes.
But this is the most general case that you may see in dynamic. So derivative of this, I have two variables. First derivative of, the derivative of r dot is going to be r double dot sine of theta plus r dot times derivative of this with respect to time, r dot theta dot cosine of theta. Derivative of this, derivative of r is r dot. I keep the refs. Then keep these two, first one and third one, differentiate this. I'm getting r theta dot cosine of theta, and last one is negative r theta dot square sine of theta. I'm rewriting this here. First term r double dot sine of theta, r dot theta dot cosine, r dot theta dot, it should be cosine. r dot theta dot cosine of theta, it's going to be 2 r dot theta dot cosine of theta. I'm writing this first, negative r theta dot square sine of theta minus plus. So this is the x component and y component of acceleration of point P when point P is moving along this general curve. Good? Now I'm going to define 4 different terms of acceleration. 4 different terms of acceleration. These two, it's going to be acceleration type 1. These two, it's going to be acceleration type 2, type 3, type 4. There are 4 types of accelerations. Acceleration type 1 has the component of x component of r double dot cosine of theta, r double dot sine of theta. So this acceleration, just compare with the point P. Point P was r cosine of theta, y of P was r sine of theta. At the beginning of today's class, I compared 2 vectors. Now compare x component of point P with the x component of acceleration of point P on the first term. Both have cosine and sine for x and y. The coefficients are different, so it's gonna tell me the first term of acceleration is gonna be aligned with this vector. So acceleration it's representing change in magnitude of r. It's representing r double dot, how the magnitude of r is varying over the time. R dot and then r double dot. So, and it's gonna be in the same direction of vector OP. Acceleration 2. We call this Coriolis the magnitude is negative 2 r dot theta dot times sine of theta for x component, and the for y component is positive 2 r dot theta dot sine of theta. Now look at this for type 2. I can write in this way. 2 r dot theta dot cosine of theta plus 90 degrees. And for y component, I can write it down as 2 r dot theta dot sine of theta plus 90 degrees. Cosine of one angle plus 90 is gonna be negative sine. Cosine of angle plus 90 is gonna be negative sine. And sine of any angle plus 90 is gonna be positive cosine. Positive 2 r dot theta dot cosine of theta, which is gonna give me the first term here and second term, which is positive. Now, if I compare this vector of acceleration with the original OP, this is angle theta, this is angle of theta plus 90. So this type of acceleration is 90 degree to the first to the vector OP. So the Coriolis acceleration is going to have angle of theta plus 90 with the magnitude of 2r dot theta dot. Make sense? Compare these two vectors. This is y component, this is x component. With this guy. Both have, this one has the angle of theta, this one has angle of theta plus 90. Cosine, sine, positive. So it's telling me that these two vectors are 90 degrees apart. Make sense? Is that clear? All right. We call this Coriolis acceleration. It's due to change in magnitude and the angular and the orientation of the vector, which is theta. And number 3, acceleration type 3, we call this normal acceleration. X component of that is negative r theta dot square cosine of theta, and this one is negative r theta dot square sine of theta. Vector OP has the angle of theta, r cosine of theta, r sine of theta. How can I change it to positive? I can say positive r theta dot square cosine of theta plus 180 degree. Cosine of any angle plus 180, it's going to be negative of cosine of that angle. For the sine also it's true. Sine of any angle plus 180 is going to be negative of sine. Now you can compare these two. Here I have theta plus 180, here I have theta. So the normal stress is going to be 180 degree up from vector OP. This is theta plus 180. So it's gonna, the acceleration is gonna be toward the origin from point P if you draw the vector from P. And vector 4, we call it tangential acceleration. Tangential acceleration with the term of negative r theta dot sine of theta, for x positive r theta dot cosine of theta. It's similar to type 2. It's negative on sine, negative on sine, positive for cosine, positive for cosine. Type 2 was 90 degrees up. From angle of head. So these are all 4 types of acceleration that you might have. And this is like, I just differentiate X component and Y component. I label them type 1, type 2, type 3, and type 4. I have type 3 normal acceleration. Here I have type 4. As a normal acceleration. Just if you just write this one first, then number 3, you will get the same thing that you wrote here. Term 3, which is going to be tangential, it's going to be term 4 for us. And term 2 is the Coriolis, same as term 2 that we derived. And term 1 is the radial acceleration. It should be normal. Term 4 is the normal acceleration. So it should be changed. So term 1, it's going to be a line vector OP. So this term, which is the radial acceleration, change in magnitude of R, is going to be a line vector OP, and it's going to present due to change in magnitude of the OP. Term 2, it's going to present due to change in magnitude of OP, which is R dot, and change in magnitude of rotation of OP, which is theta dot. And it's going to be 90 degrees off from vector OP. Vector term 3, it's going to be this guy. It's 90 degrees off, and it's occur when we have change in angular velocity of OP. And term 4, it's going to be term 3 here. It's 180 degrees off from OP, and it's going to show up when we have change in rotational angle. So if point P is here, rotating at constant angular speed, omega, which is theta dot, is constant. If point P is moving along the circular circle, which terms they are going to get 0 value? The last one is getting 0 value. So we are going to get the value for 1, 2, and 3.
No, the last one is going to get R is a constant to
R is constant because it's running in a circular path. R length is not going to change.
So the first, the second, and the fourth?
The first and second one is going to be 0 because R dot is going to be 0. R double dot for sure it's going to be 0. So these two terms, they are going to get the 0 value. I said it's running at the constant speed. So meaning theta dot is not varying with time. Theta double dot is going to be 0. So only term 3 is going to be there, which is going to be normal stress, normal acceleration, sorry. Any question on this? All right, let's difficulty-wise, displacement analysis is going to be the most difficult, then acceleration, and then velocity is going to be in order, because acceleration, when you want to differentiate, it's going to have more terms than velocity. So let's start with the first mechanism, which is offset slider track. We would like to differentiate acceleration equations. B, C, A, and B. When you want to perform acceleration analysis, you have to perform position analysis first, and then velocity analysis, and then you are ready to do acceleration analysis. You cannot derive the acceleration equation without doing the velocity and position analysis. So for displacement analysis, if you remember the constants, we had constants, variables, noun, and unknown. Constants for displacement analysis of offset slider crank were A, the length of the link 2, link 3, and the offset was given. The variables, we had two rotational link, which is theta 2 and theta 3, and D, the location of the slider was variable. Nouns were constants plus theta 2, 1 degree of freedom. One of the variables should be noun. The remaining were theta 3 and D. So for velocity, constants are the same. Variables, whatever was variable in displacement, just put a dot on top of that. Angular velocity of link 2, angular velocity of link 3, and the speed of slider, theta dot 2, theta dot 3, and d dot. And nouns, constants, we have performed displacement analysis. So theta 2 is given, theta 3, and d. From displacement analysis, and theta 2 was given on displacement, its derivative should be given on velocity analysis. So theta dot 2 should be given because degree of freedom is 1. And we are solving for, just put a dot on top of the unknown terms from displacement, and we will get theta dot 3 and d dot as new unknown. For acceleration, constant will be the same. Variables, whatever was variable here on velocity, its derivative with respect to time should be considered as a new variable. So put another dot. Angular acceleration of link 3. Angular acceleration of link 4. And acceleration of the slider. Or second derivative of theta 3, second derivative of theta 4, and second derivative of displacement. Nouns would be constant plus theta 2, theta 3, and d from displacement analysis. From velocity analysis, theta dot 2, theta dot 3, d dot, plus degree of freedom is 1, theta dot 2 is given on velocity, theta double dot 2 should be given because degree of freedom is 1. Without knowing this, you cannot solve for theta double dot 3 and dw. So the remaining would be the new unknowns. And we are solving for theta double dot 3 and dw. Alright. Any questions so far? Again, we start from displacement analysis. We write the x component and y component for the vector loop. It's going to be a cosine of theta 2 equals to d plus b cosine of theta 3. A sine of theta 2 equals to c plus b sine of theta 3. Displacement. For velocity, we differentiate this with respect to time. We differentiate this with respect to time, we differentiate to the right hand side with respect to time, we end up to these two equations. Negative a theta dot 2 sine of theta 2 equals to d dot, and negative b theta dot sine of theta 3. And for this, it's going to be a theta dot 2 cosine of theta 2 equals to b theta dot 3 sine of cosine of that. This is velocity equation. So as class activity, differentiate or derive the first equation of acceleration analysis. Differentiate this with respect to time. Work on this. Number 4. What will be the first step? What will be the first step on the first equation?
Which equation?
This one. You were supposed to differentiate this with respect to time.
Okay, so is it
What do you think? Is the length of A changing with time? So it's not changing. We keep it as a coefficient.
Yeah.
We go to the second one.
So there will be negative a theta 2 double dot. Sine theta 2.
Sine of theta 2. Okay.
And then derive the sine theta 2. Gives us negative cosine.
It's gonna give me theta dot cosine of theta 2.
And then
The right hand side.
b double dot minus b theta double dot sine theta 3. And then minus cosine
Minus b theta dot 3 derivative of this guy, which is cosine of theta 3 times theta dot. You already differentiate this guy and this guy. I mean, this constant derivative of theta dot is theta dot dot. Derivative of this is cosine of theta 3 times theta dot.
and then minus theta 3 dot sine cosine.
Cosine, yes. Thank you. So we continue on Wednesday class.